Good day, everybody. Today we're going to be looking at the reflection of light, which is the first section in our unit looking at how light works and how it is similar and different to other things that we have studied in this class. So let's kind of go ahead and get started. I want to start with a little bit of a comparison and contrast between sound and light because they are both, they have a lot of similarities to them, but there's a couple things that kind of stand out as making them different. And so some of the similarities that you should know about sound and light is that they are both waves. Let me switch so that you can read. There we go. They're both waves. So they both are going to have behaviors like reflection, refraction, and diffraction. Light is going to do all of those things. We can talk about things like frequency, wavelength with light. All of those things that are common for waves are also going to be something that we see a lot with light. And so those are things that are how they're similar to sound waves. The key difference, though, between them is that light is what we call an electromagnetic wave, or it's an EM wave, which means that the medium that light travels through is the electromagnetic spectrum. It doesn't need a physical medium to go through. I can send light through a vacuum and it will be just fine, which is why we get light from the sun and it has to travel through the vacuum of space. Sound can't travel through a vacuum because sound is a mechanical wave. And that's going to be one of the biggest difference between these two things is that light is able to do things that sound can't just because light doesn't require something to travel through. It's able to kind of go through on its own. So let's kind of go ahead and get started. How is light different from sound? Like I said, sound is what we refer to as a mechanical wave. It requires a physical medium to pass through. As I'm recording this lecture right now, the sound of my voice is traveling through the air towards the microphone. Light, on the other hand, is an electromagnetic wave. It does not require a physical medium to travel, and it can move through a vacuum, like moving through space. Again, sunlight is able to move through space because it doesn't require a medium for it to travel through. It can go through the empty void of space easily. Sound cannot. So if I had like an explosion happening, the sun is a good example of this. The sun is a giant explosion in space. And you know what? Let's go with the color scheme. If we had a giant explosion in space like the sun, and it's shooting out its light rays, but it's also shooting out sound waves, one of those two things is able to travel through space, and it's because light is the electromagnetic wave. If you could hear the sound of the sun, even at the distance that it's at, it would be the loudest noise that you could possibly hear, and all of us would go deaf because the sun is just a giant explosion. But we can't because sound is a mechanical wave and it cannot pass through a vacuum. So light still has the behavior of a wave, though, even though it is an EM wave. It's going to undergo reflection, refraction, and diffraction. It's going to be able to bend around objects. We can change its direction using something called a prism. It goes through holes in doorways and spreads out on the other side using diffraction. So all of those things that we are used to for waves are still going to apply here. So before I kind of jump into light in general, I want to go over kind of the basic principle of how we see things. And so let's say that there is a light bulb hanging up in a room. Here's my light bulb. Here's the little filament inside of the light bulb. And there is an object that somebody is trying to see. Like, I don't know, here's a dog. Has ears. All right, so this is a dog for those of you that can't read stick figure. All right, and there is a light bulb here, and let's go through the process of you being able to see a dog. So in order for this to happen, a particle of light is going to leave the light bulb and it's going to hit the dog. And when that light bulb hits the dog is going to give that light, or that particle of light, some information about itself, and then that light leaves the dog, it bounces off of the dog, and it travels into the eye of the person. And our brain interprets that information from that light and figures out what we can see. So if you kind of look around the room right now, all of the information that you are getting about your space, the TVs on the walls, the color of the walls, what's on the ceiling, all of that is happening because light is leaving a light source. It's bouncing off of an object, and then that light, after bouncing off the object, is going to run into your eye. And if I break this cycle up in any way, we won't be able to see something. So in order for us to see an object, light from a source has to bounce off an object and get into our eye, which means we are only seeing whatever is reflected by the source. If I created a dog that was 100% absorptive, so this dog was able to absorb light and nothing reflected off of it, we wouldn't be able to see the dog. It would be like the dog was invisible, because the dog is now absorbing all of the light and nothing's leaving it. If I was to put something up between the dog and the light so that no light was able to pass through it and hit the dog, now there's no light being able to get to the dog, and so again, we won't be able to see anything because that light wasn't able to reach the object. So light, when it comes to us seeing things, light carries information, but it can only carry information about things that it is able to bounce off of. So that's kind of how vision works, which means everything is about reflectors. Going back to our principles of thermal physics, we talked about reflectors a little bit, things that were able to reflect heat energy, more specifically. And we had some characteristics that we like to say. And so good reflectors, if you remember, good reflectors are shiny. They tend to be smooth, if I can spell that correctly. There we go. And they are easy to see in the dark. So if you think about kind of the reflective gear that you might wear if you were out riding a bicycle, for instance, in the middle of the night, you're going to want to wear something that's light in color. Oops, don't know why that happened. Let me see if I get that back. I guess I can't. So we're going to go light in color, preferably shiny, and preferably smooth in texture. So these things are going to be good reflectors. And so the reflective tape that you see, that is all of those things. If you were to wear a dark, like a dark colored matte hoodie that just kind of absorbs all of that light, that is the worst thing you can wear at night if you want to be seen, because it's going to absorb the limited light there is, and none of it's going to be able to bounce off of you. Now, reflections are obviously things. We see reflections and we understand what they are intuitively, but if you were to look at this kind of image of this city right here, you might be like, oh, okay, there is clearly a city above the water, and if I look, I can also see that there is a city below the water. And our brains are already kind of attuned to the fact that this section down here, there we go, this section down here, we know this is a reflection. We know that there isn't some kind of secret city underneath the water. But but if you kind of objectively look at it, it certainly can seem like there's something under the water right there. And so this is what we refer to as a virtual image. Okay, a virtual image is an image that forms where light rays look like they're coming from, but we know that there isn't anything there. So for instance, this is a picture of a bird looking at a mirror. The image of the bird, we know that there isn't actually a bird in the mirror. It's an illusion. It is an image. You couldn't reach out and actually successfully touch the bird through the mirror. And so we say that this is virtual. Kind of like virtual reality is a reality that isn't real. We use the word virtual to mean fake. Now, if I was to project an image onto a projector, I can walk up and I can touch that image, and the object the light is coming from something that I can actually touch, that would be an example of a real image. So real images and virtual images are opposite. One comes from a place where light can't actually be coming from, like a mirror. The other one is coming from a place where you could physically go up and touch the object that you're looking at, like a projector. And so real and virtual images are going to be something that we have to keep track of when we're thinking about what are we seeing and how is this reflection working. Now, earlier I talked about something called the law of reflection. This was a couple of units ago, but I'd like to kind of hit this again. So we've got this idea that light is reflected at the angle. How it's reflected is determined by the angle that it hits the reflective surface at. And so when we have an incident ray, which is a ray that's heading towards the mirror, we can measure the angle of incidence from something called the normal line. And you can see that the normal line is this little dotted line in the diagram. And our angle of incidence, which is the green angle right here, is going to be always equal to our angle of reflection, which is our blue angle. So those angles have to be the same, which means if I increase my angle of incidence, it will increase my angle of reflection. Those things have to be equal. I'm sorry, I'll get that text on there so you can see it for your notes. And both of these things are measured from the normal line. And this is a mistake that I see students make over and over again. We're not measuring from the mirror. We're not measuring from the incident ray to the mirror. We're measuring from the incident ray to normal. And that's drawing a normal line is going to be key to understanding how diagrams are going to work for this section. So there is an activity here where you should be able to identify where each of these 5 items is. I will leave that up to you to check your answers. Here is the answer right here. And then the last thing we're going to look at is something called the critical angle. Okay, so the critical angle determines whether light is able to move from a more dense substance into a less dense substance. Let's say that I'm trying to shine a laser out of water and into the air, like if I was at the bottom of a pool. All right, there's a chance that some of that light is going to reflect off the surface of the water and not make it into the air, and that chance is determined by what's called the critical angle. So if light hits the surface, depending on the angle that it hits, some of it might leave, some of it might not, and that angle is called the critical angle. And I'll give you an example of this. So here's an example, and our critical angle determines whether light leaves or not. And I like to say that the critical angle is like a door. So if you are inside of the critical angle, that means that the light gets to leave the surface. So if I'm looking at my colors right here, switch to my black pen, my 2 colors, if I'm starting inside the glass and I'm moving out into the air, the 2 colors that get to leave are green and yellow. And so I know that these are inside of the critical angle because just like a door, if you're inside of the door or the door frame, you get to leave. Now, I do have one color that kind of makes it to the edge of the glass and then stops, or it just goes along the edge like that. That's like trying to walk through the frame of the door. Like part of you might make it through the door frame, but not all of you. And so I would say that my red line is equal to my critical angle. Now I've got 2 colors. I've got this teal color right here and the dark blue. These bounce back in. And so these are outside of the critical angle, like trying to leave a room without using the door. You just run into the wall and you stay inside of the room. And so this is what we refer to as total internal reflection, because these objects are not able to leave. And so kind of summarizing that right here, the critical angle is measured from the normal line, and it is different depending on what the light is shining through. So that critical angle can change a little bit. But light shining at an angle inside of the critical angle gets to escape the medium, like leaving through a door frame. Light at the edge of the critical angle will partially escape. It kind of skims along the edge of the top, how do I want to put, like the top of the prism, like in my previous example. And then light that is outside of the critical angle reflects back into the medium and it's not able to escape. And so that is the critical angle, and that is going to be the last thing that we go over in notes today. Here is a list of a couple summaries I would like you to have, and I'll see you in class.